Awesome. So let's move on to the 5 V's. We call them 5 V's of big data. If you literally search Google this 5 V's of big data, you will get these 5 V's as the first search result from Google. So first V is velocity. What do we mean by velocity? Anyone want to take a stab at it?
At very high rate, the data is being captured or collected at very high rate. Sorry.
This was KK. Sorry, please raise hand before speaking. I'll call out the name and then you can speak. So just to avoid the confusion.
Yeah,
okay, so KK said that at very high speed, the data that we get. Okay, perfect. Yeah, next comes the variety. Shrikant raised hand. Yes, Shilja, please. Okay, Shilja went on. Okay, Shilja raised now. Okay, yeah, Shilja, go ahead.
Pace of the data, how data comes quickly, or what is the pace of the data?
Correct, that's velocity. Perfect. So we all understand that. Yes, Mithilesh, what is variety?
Types of data, like it can be like CSV and Parquet format data, kind of that.
You went into literal extensions, but right now I would like to recall someone, actually Mihir highlighted like unstructured, semi-structured, structured data set, right? Basically, yeah, broad category are that. Then within that, what Mithilesh is saying, these extensions fall into those categories. Thanks, Mithilesh. So that's variety. Now comes the volume. KK.
One more thing I would like to add for the variety. Does it mean lots of data point is being collected like in sensors or in IoT devices? They collect a lot of data point, 1,000 data points for a given time.
Oh, right now, correct. Right now, we are not talking about variety of sources, like from which it consumes we get the data. Right now, we are talking about the data set type, like kind of data that we have, different type of data set that we have, that is structured, unstructured, semi-structured. Broad categories. Within that, then there are further extensions, further even split classifications are there. But yeah, that's for the later part.
So that's like variety comes like images, audio, and all those things comes under variety, right?
Everything is data. Yes.
Yes.
Everything is data. So even image data, spatial as in SPATIAL, not SPCIAL. SPATIAL, spatial data also falls under a variety of data. But that's basically, you can say, semi-structured data. Even image is a semi-structured data. Actually, image right now, as per today's definition, image falls under structured data. But let's take in semi-structured if you want. Yeah, let's go with spatial and image. That's semi-structured. Mihir, you are on mute. Tell me, what is volume? Okay, I think he's unmuted by mistake. Shrikant, go ahead. What is volume?
Maybe it is like a quantity, like the data quantity that we have.
Correct. I mean, this is basically the second definition. The second line of our definition, right? Cannot store on a single machine. Then comes again, I'm telling you, this is the spelling is incorrect. Do not go by the spelling. Excuse me for that. It is veracity. 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 I think Shelja highlighted a point of accuracy, right? I am pretty sure it was Shelja. Yeah.
Yes,
so
sure.
Shelja, this is that. This is the fourth V of 5 V's of big data, where you basically take truthfulness or accuracy of the data into account. And then fifth, and the most important of the big data V is value. The value in terms of business value, or the value, you can say, you must have all heard, right? Facebook is selling your data, or some XYZ company is selling your data. Some scam happened because of this data. Who was that guy? Donald Trump became president because Cambridge Analytics bought data from Facebook and then started a campaign. So that's value of data because of which people are selling and buying. So that's most important. But this is this value V has been added recently in recent years, let's say last couple of years. Otherwise, traditionally there were 4 V's of big data. If you will search 4 V's of big data, you will get only the first 4. When you search 5 V's, you will get value also. Then there is, I guess, 6th V, which is called variability, which is not so important and you can ignore, and that's why I have not even added. But yeah, so far the definition has been extended to 6 V's just to be on the same page. But yeah, 4 V's are important. 5 V's is good to know. 6 V's is basically, yeah, if you know well and good, it's not, it's fine. You can just forget about it. But 6th one is variability. Now, just to be on the same page, when we say velocity, right? Velocity means at the pace we are getting. But how rapid this pace could be? I mean, why it is so important to consider velocity in terms of big data? Anyone tell me that? Can anyone help me with that? Yes, Akshay, your hand is raised.
Like the speed with which we are like handling those data.
No, but I'm saying why it is important. Let's say I get data once a year. Can that still contribute to a big data thing?
Maybe like for real-time processing or streaming purpose, the processing velocity of data is important.
No. So I'll tell you. The thing is, remember I said streaming data set. Okay, let's come to the streaming data set part first. So, excuse me. Right now, let's take we have whose JSurya system, which has 2 TB of RAM and 14 gigs of processing space as of now. Okay, for us to do work upon. But what I did was I just basically deleted everything from a system, and now we have whole 2 TB of space, and I have 1 GB of data file. Okay, to process, and that is residing on JSurya system. Now I say that JSurya, it is a big data, your system won't be sufficient. Now JSurya will ask me how. Correct? So what I say that JSurya, the way I received this particular 1 GB file is, this was the data created by a log server in a enterprise environment, and that log server is capturing logs from, let's say, 100 of firewalls, and it was just generated within a minute. A 1 GB file. Let's say we have that dumped in as a CSV. So he asked me, okay, but it's still we have 2 TBs, another 2047 GB is there. So I was like, that's true, but can you divide 2047 by 60? So how much is it? Let me open calculator. So 1 GB is already there on the system, and then 2047 GBs are available. I divide it by 60 and I get 34.11. Now let's say I round it off till 35. I divide 35 by 24. 1.45 days. Within 1.45 days, JSurya's 2 TB hard disk will be filled with data. After let's say for 1.5th time of day, let's say till 35 hours, right? Till 35 hours, his hard disk would support us and will be able to capture the data from the source. Whenever the 35th hour, 1 minute starts, his hard drive will give the error that space is full, we cannot store any further data.
Shubham, can you please explain this point once again?
Yes. So let's say JSurya's hard disk has 2 TB of space, right? 1 TB is 1024, multiply by 2, 2048, correct? Now, what I did was I asked JSurya that I have 1 GB of file. And when JSurya says, yeah, sure, 1 GB is fine. I have 2 TB of space, you can store it. And it's not big data. I said that, no, it is a big data. So first of all, space available to us in JSurya's hard disk is -1, correct? Which is 2047. This is the space available because we already have 1 GB of data. Now he asked me how it is one big data. JSurya asked me. I say that, okay, the way it is big data is this 1 GB file that we have received is a 1 minute logs from a log server. A CSAM log server, it could be any ASIM log server, it could be. But what I'm saying is that it is a log server which is capturing logs from hundreds of firewall in an enterprise system. So hundreds of firewall in an enterprise system is generating 1 GB of logs within a minute. And that's how we are getting that file. Now, we have initially stored that file, which has captured data of, let's say, 1 minute. Now, what I do was, I tell Surya that, hey, it is big data. And he asked me how. I say that, okay, the way it is big data is because 2047 is GB is available to us, but we are getting 1 GB in 1 minute. So we will get 60 GB in an hour, right? 60 GB in an hour would be 34 hours. So within 2047 GB, you can store 34 hours of data, 34.11 hours of data. Now, when I divide this 34.11 hours by 24, that is 1 day, I get only 1.42. So within 1.42 days, J Surya's hard disk will be filled and will be out of space. And that's why I was calling that J Surya, no, this is a big data because of the velocity. Because every 1 minute, we're going to get 1 GB of data and we'll be running out of space within 1.42 days. And we won't be able to further store it, let alone process it. Let's forget about that. We won't be even able to store it on our system. So that's how velocity contributes to the big data. Because his space, I mean, J Surya system has 2 TB space. We currently at hand have only 1 GB of file, but within 1.5 day, the system, the velocity at which we are getting this data will make it a big data for his system. Is that clear now, Akshay?
Yes, sure.
Any questions, anyone? How 1 GB of file can be big data for J Surya system? Got it. Okay, awesome. So velocity is clear. Now comes the variety. How come variety could be the big data, right? So variety, when we are talking about variety, we are talking about structured, unstructured, semi-structured, and structured data set. Now, the way variety contributes to big data is, someone was talking about traditional system, right? We won't be able to process using traditional system. And I said that that is partially correct. So there, that particular actually line contributes to variety. So let's say I give you, so J Surya system we have, it has CPU and RAM, like say 14 gigs of RAM, latest, let's say server grade Xeon processor, Intel Xeon processor. Let's talk about that. Now I give him unstructured data, all 2 TB unstructured data. We are able to store it, but we do not have a system, or let's say unstructured data. How would you process unstructured data is what then the question be. Relational database system, RDBMS, as like by using Microsoft SQL Server, Oracle Server, you can process it. Then unstructured data like JSON format or something else, you will be still able to, let's say, process using what do we call it? Sorry, by using any language. You can take JavaScript or Python, just load the JSON object and you can process the unstructured data also. But unstructured data, how would you process that? The reason here unstructured data processing becomes the challenge is, in order to find pattern and make unstructured data into a semi-structured or structured, we need to see the data at once. We need to find the pattern. In order to find the pattern, in order to do the data mining, we need a lot more data than 14 gigs at a time in our memory. Because if we take 14 gigs at a time in a memory, what was the calculation? Let me do that. 2048 divided by 14 gigs. 146. So we will be using let's round it off to 146. We will be using 146 batches to do the data mining and find the patterns within the data. We can obtain 146 different patterns. Again, that is basically coming back to 0 because we haven't getting 146 pattern is same as getting no pattern. A pattern has to be consistent. In order to find a consistent pattern, you need to process a lot more data than 14 gigs at a time. At least, let's say 250 gigs. When I do 250 gigs, over 8 divided by, instead of 250, I'll go with 256, and it will give you 8 patterns. This is still close. We can find like similarity with out of these 8 patterns, even if 2 or 3 patterns will match, right? We can say that yes, at least 1/4 of the data have this consistent pattern. But getting 146 pattern is same as getting no pattern at all. And that's how variety defines or helps or contributes towards defining big data. Any questions? Just so you all know, you cannot process unstructured data. When I say you cannot process, unless and until you know what the data has or how we are getting the data, what is the pattern. Can anyone tell me how we will be able to process? So it's a myth when we say that. Actually, it's not a myth. It's a terminology that we use, that unstructured data is getting processed in big data. No, what we do is we take unstructured data, we find patterns, we find the, you can say, data template or the schema, or at least what is useful for us. We just take that out, convert into semi-structured or semi-structured or structured, and then further process it. That's how we are leveraging unstructured data. Nobody in its native form is able to use unstructured data. The reason I was calling, what do you say, image data as semi-structured data, because image has a resolution size, right? Let's say 1048 by 1048. So we know that these are the pixels, and then each pixel will have RGB value, red, green, blue value, due to which we are able to see that this particular pixel has this value and this image is forming. So that's not an unstructured data, that's semi-structured data. We know the structure, and that's why we are able to process an image. If we don't know the let's say resolution of the image, if you take 1048 by 1048 image and try to process it with the, let's say, vector of a lesser size, let's say take any like 512 by 512, then half of your information will be missed, and the final processed image result you will get will be absurd. So you're getting me? You have cropped the image randomly and then processed it, so the result will be garbage. So it's very important for you to know what is the pixel size of the images that you're getting. Akshay, you want to say something? Here, I think it's by mistake. Yeah, so that's how an image becomes semi-structured or structured, but not unstructured. And that's why we are able to successfully do computer vision and image processing algorithm and techniques at R&D due to the semi-structured. We cannot process unstructured data. Even logs are separated by pipes. So there is still. Akshay, you want to say something? Hello, Akshay? Yeah, I'm not able to move this guy. Oh, I'm not able to move this guy now. Akshay, are you there? Okay, I think it's silent. We can ignore for now. Yeah. So when I was at variety. Yeah. Any question related to variety? How variety contributes to big data? Anyone? Just say no in the chat if you don't have any question with respect to variety. No. The question is no. I need 2 more no's to go ahead with volume. Shivanshi says no. And 1 more no. Shrikant says no. Perfect. Volume, self-explanatory. You all know. Volume contributes to big data. Second point itself, cannot store on a single machine. And that's how we know that volume contributes. Now let's come to veracity. Veracity, the truthfulness or the accuracy of the data itself, contributes to big data. How? The way it contributes to big data is, so let's say I give you 100 GB of data, and I say that this is coming from some, let's say, operating system logs. These are operating system logs that how this showcases when the system was on and when the system was off. I say that 0 is on, 1 is off, and we are getting these 0 and 1s and 0 and 1s, and we have the file of 100 GB with the 0 and 1s. Now I told you that 0 is off and 1 is on. Correct? You did some data mining and you get to know, okay, half of the time the system is off and half of the time the system is on. Not half, actually, let's take 60-40, like half of the 60% of the time this is off and 40% of the time it is on. Let's go with that. But the way this truthfulness or accuracy accounts for big data is that 100 GB of data becomes garbage as soon as this is vice versa. Like 0 is off and 1 is on, and I'm telling you the vice versa. It becomes garbage. So it's very important the data that we get is correct, is true to its source, so that we can draw some analysis on it. Because the problem here is the way it is contributing to big data is we cannot delete that data. Why we cannot delete the data? Because we don't know what is the correct thing. At least we have the data, it's just that we don't know what is it. We don't delete it because our question will become, what is the correct thing? And that's how it contributes to big data, because it's there, but we cannot use it. But at the same time, we cannot delete it. So it's there in our memory, in our storage, but we cannot leverage it. And that's how veracity plays a role in big data. So it's very, very important that no matter how small or how big data set you have, you know what is the true source of it, what is the pattern, what we are getting exactly, so that you can further analyze or have, you can say, do data mining task or get something out of the data. Unless and until you don't have those kind of insights, neither you'll be able to delete it, nor you'll be able to process it. So that's how veracity contributes to big data. Any questions on this?
I didn't completely quite get the concept, but shall I try to summarize what I understood? Is it something like, when we are not sure how to use the data, is that the factor here?
Yes, okay. Something like that, correct. When you don't know how to use the data or what is the data that you're getting and you're not able to use it, you simply do not delete in today's world, because we know that data is the fuel. It's just that since we have the data, we don't want to delete it because we just don't know how to use it. If we ever get to know how to use it, it will be an asset for us. And just because of that thinking, we won't be able to delete it, neither will be able to process it. And we'll be having that data which will be occupying space, but it's not usable for us. And that's how veracity contributes to big data. If let's say a data that let's take another case. There is a, let's say, 2 TB of data, and we know what is the source and we know whatsoever the thing is. But the problem is that 2 TB of data and we are not able to find a single pattern. But we know that this data is 100% correct. 100%. But we are not able to identify a single pattern in that data. We still won't delete it because we know that this data is correct. Right now, we might not be able to use find a pattern or something like that. But what if I give you some X data set with that Y, along with which you might be able to find some pattern, and then it might become usable. You getting me? So I've given you now an example in both the cases, false, true, and false both. If we don't know, and when we don't know and when we know, in either of the cases, veracity plays a key role in defining big data. And then the fifth one comes the value. No matter how small or a big data size you have, if the value is 0, that data is 0. So we won't be storing it, and it won't be even if it would be a big data, it is of no use to us. It won't become a big data for us because we are not bothered about it. It's a garbage. But even if, let's say, we have 1 gig of, let's take the Studio example, we have 2 TB of storage, but and there is someone is telling me the data of 3 TB, and I don't even have storage, but that data has value to me. I'll still buy that big data and would try to afford it anyhow, like by either doing horizontal scaling, going to cloud computing, or doing whatsoever. to store that big data and process it and get insights out of it. So values again, if you ask. Any question related to these 5 V's?
So basically, we can say that these wheels are related with some difficulties, and that are basically contributing in the big data.
Correct. That's how they define big data. That's how these 5 V's are essentially becoming the 5 pillars of big data, defining big data. So I hope we know now what is big data. If someone would ask us what is big data, how do you define big data? What are the key points to, you can say, bifurcate whether the data is big data or not, or how do you even say that if it's a big data? We know all of these, we can answer all of these questions. Anyone has any doubts? I need 3 no's. Rupesh is 1. 2 more. I mean, if you have any questions, feel free to ask. Okay, Shrikant is no. Okay, I have got 1 question. Selja, okay, Shivanshi says 3 no's, but yeah, we have a question. Having a doubt, what is the key difference between big data and cloud computing? Oh, okay. Okay, Shelja. Big data is like restricted to just the data size that we're talking about. I mean, how to define big data. Whereas cloud computing is an architecture. I mean, these are 2 different apples and oranges. They don't have nothing in common. But I mean, I'd say only thing in common is that you can process big data with the help of cloud computing with the traditional system. You don't need any fancy Spark or something like that, because cloud computing gives you unlimited compute and unlimited power. You don't need a new system to process your the big data. You can process your big data using traditional system of RDBMS on cloud computing, because it gives you that kind of power. Now, but cloud computing, if anyone has also this question, if anyone else has this question of like, what is the difference between big data and cloud computing besides Shelja?
Shubham,
Yeah.
if cloud computing itself is providing the traditional methods to perform on big data, then what is the advantage of big data
Okay. First of all,
over
big data,
cloud computing?
yeah. Big data is concept. Concept as in concept to process big data is actually when you talk about big data as in terms of what is big data. Cloud computing, on the other hand, gives you unlimited compute and unlimited power as in the form of an architecture that you don't have to establish. It's there available to everyone at 1 click. Now, if you have cloud computing, why you should go with this traditional method is that's your question, right? Now, the problem with that approach is it's a pay-as-you-go model, correct? As your data increases, you would like to increase the compute and increase the space, correct? But the problem with that is your cost will also increase. So right now, let's say you have 10 TB of space, 10 TB of data, and for that you might need, let's say, 100 GB of RAM, correct? And it will cost you around, let's say, $1,000. Now tomorrow you have 20 TB. Now it will cost you $2,000. Now that 20 TB became 1 petabyte.
Okay.
Now it will cost you $1 million. Does that sound scalable?
No.
That's what gonna have. That's what gonna happen when you go with cloud computing and keep using traditional system to process big data.
Okay.
The reason we are going with big data is so that cost does not increase. Existing processing power we can leverage to the maximum in such a way so that cost does not increase and we process the data within the same amount of, you can say, memory and space.
Okay.
Also, when we are talking about cloud computing, right? Cloud computing, traditional system. Let's take the relational database system. Let's say we have 3 TB of relational database system file. Let's say a SQL server down. Okay. Now, when you store that 3 TB of SQL, when you build on cloud, when you build a SQL instance, right? Azure managed SQL instance. then your SQL Server need to have 3 TB of space in order to process that data. Correct?
Right. Yeah.
And a SQL Server instance of 3 TB will cost you around at least, if not less, $2,500, I guess, per month.
Okay.
Okay. But when we talk about big data, we do not store data in a traditional system like a SQL Server, even if it is relational or unrelational, non we do not store it in a traditional storage of a SQL Server table tabular structure file. Instead, what we'll do is we will get a dump of that data into a CSV, or let's say some other file format, Parquet format, which someone else listed, and we will store it on a data lake, Azure Data Lake storage, which is a much more cheaper storage option. Like in I think $10 or $15 a month, you can store 3 TB.
Okay.
That kind of difference we are talking about in cost. That's why big data became prominent, and big data processing tools like Hadoop, Spark are getting used widely instead of just relying on cloud computing power, where you can get traditional power. You can enhance your traditional system's power just by a click.
Okay, got it. Yeah.
Yeah. We will going to talk about that in detail in next slide. Yes. So now basically the big data processing chunk, big data processing system have a typical divide and conquer concept. Divide and conquer. But as the name suggests, we are just dividing the data into multiple chunks and processing it parallelly or serially in order to get the maximum out of it. First point says, big data is an issue and hence it needs a fix, which is nothing but a distributed file system, which someone said, right? Distributed file system. So here your definition goes. I said it is partially true, not exactly. That's the reason. Simpler terms, divide and conquer. Instead of keeping the complete load on one single system, we are going to delegate multiple systems to do the job. So right now, JSurya has a 2 TB system, and let's say I also has a 2 TB system. Now we get a 3 TB file. In order to process that 3 TB of big data, what we're going to do is we're going to store 1.5 TB on JSurya system, 1.5 TB on my system. And now we again do not have a big data problem. And now we can successfully, you can say, store and process that data. So, I hope it's clear how divide and conquer is like coming into the picture. The problem of big data with respect to, so 3 TB was a big data with respect to JSurya system. But as soon as I bring my system into the picture, that 3 TB is not a big data anymore. And now we can successfully mine, and JSurya system can successfully store that 3 TB of data and process it. So we have solved the big data problem. Now, how does that divide and conquer look like? So there's, let's say, initially there was a single machine with 4 IO channels and 100 Mbps. And now we have so many machines. Let's say, how many are they? There are 10 machines. And this is 1 TB of data, right? So now if Shelja was right. Yeah. Shelja, according to, let's say, traditional system, if we take that 1 TB of data and we try to store it, use it on, like, process it on this system, right? The processing will happen serially, like one by one.
Okay.
Right? 100 Mbps batches will be created and it will happen serially. So let's say 100 MB divided by 1 TB, whatsoever would be the number of batches. And if you're taking one batch of 100 MB will take 1 minute, that will be a number of minutes that it will take to process, which is a huge amount of time, correct?
Yeah.
Now the way, okay, 100 TB, if I divide it by 100, it will become what? 10 GB, right? Correct. 10 GB, if I multiply by 10, 100 GB, if I multiply by 10, 1 TB. Correct. So it becomes 10 GB. 10 GB is nothing but, oh no, that's, 10 to the power 8. 10 to the power 8 minutes around 10 to the power 7 or 8, I'm not sure. Yeah. That kind of time we are talking about to process 1 TB of data on this system. But what if we have 10 such systems? Now this amount of time will be divided by 10 here, because we have 10 systems which can run in parallel and process this 1 TB of data. So we'll create these 100 MB batches, send it across these 10 different systems, process them parallelly, which will reduce the time 10 times by 10 times. And that's how you process big data and optimize and use it in an optimum manner. The way we are able to see that this is a single machine and these are multiple machines, it does not essentially mean we are talking about hardwares. So I'm not sure how many of you have used VMs, virtual machines.
Yeah, I have
Yes,
used it.
we have. I have.
Perfect. Perfect. So on your system, you can create like one single 100 and like a small machine, a small VM, and then you can create 10 VM. So the 10 VM thing is what we call a cluster. So we have a cluster of 10 VMs, and this is just a single VM, standalone VM. So when you process the big data in a standalone mode versus the cluster mode of this 10, you can check for yourself literally that the time is reduced by 10 folds, 10 times basically. Because you have, I mean, 10 VMs running parallelly, processing the same amount of data parallelly, not serially. Okay. So that's how we are talking about the divide and conquer comes into the picture.
One thing I like to discuss, Shubham, here.
Sure.
Like the previous slide, I think this divide and conquer basically comes when we have a low cost community hardware servers
Yes.
that we can add in the parallel with our current machines.
Yes. That's
Right?
true. That's true.
That is the
Because
concept.
we don't want to increase the, I mean, it's easy to say 10 machines, but cost of one machine and cost
Right.
versus cost of 10 machines will be 10 times more, right?
Right. Yeah.
So again, we don't want that. We are talking about commodity hardware that is already available at hand with us. It's just that we are not leveraging it in this sense, where we are creating a cluster and using it for distributed computing. So what I'm assuming is that there is no additional cost. This one system versus this 10 system is just that 10 systems were available to you. You were using only one system because you didn't know how to divide and conquer the data and do distributed processing. Right now, that 10 systems were available. It's just that you didn't know the concept of Hadoop and let's say Spark of distributed computing for that matter. And that's why you were relying on one single system. But since 10 systems were available to you, now I'm assuming that since let's say now I've given you the power of dividing and distributed computing, now you are able to leverage all of those 10 systems together and process your data in a much faster sense. Okay.
Yeah, got it.
Perfect. Now, this diagram is a very neat representation, although it does not look that neat within the Hadoop architecture. But yeah, essentially the Hadoop architecture have a master slave system. So there will be a master node or what we call as name node, and then there will be slaves, which will be called as data node. So these master node and architecture of this master slave architecture of data node and name node will essentially perform the task of this distributed computing in a clusteral sense. This is not a very, I mean, neat diagram in terms of Hadoop. It's just a generic distributed file system diagram, you can say. It's not Hadoop distributed file system diagram. It's a distributed file system diagram. Please note that. Do not confuse it with Hadoop. This is not Hadoop, to be precise. Otherwise, here it would have been written as name node, and these would be written as data node, then the secondary node and whatnot. Let's move on to the next one. This is just a we can say a reference for a distributed file system. Whomsoever knows doesn't know how does a distributed file system work. So before Hadoop, also distributed file system did exist. Just an FYI, Hadoop came into the picture, I guess, in 2008. Let me Google it for you. Hadoop creation date. Okay. It was like 2005. So even before 2005, distributed computing did exist. Hmm. 1970s. See, like it took us 35 years to even after come from distributed computing to Hadoop. This is nothing but an enhancement over distributed computing. So this diagram that you're able to see, this is just showcasing the traditional distributed computing system.